Okay, good afternoon. Today we will continue with our discussion with processes. So we had started with processes and we have covered some topics about processes. And we have seen how we can create processes and how we can enable the process to communicate with each other. For that we have seen one method, which was shared memory. And now we will see another method, another mechanism that can be used to enable processes to communicate with each other, and that method is message passing. So we will discuss message passing today. Message passing is another IPC mechanism. Just before discussing that, let me briefly remind you what was the other mechanism that we could use. So the other mechanism that we could use was actually the shared memory approach, okay? In that we could create a shared memory between two or more processes, and process can access the shared memory and read and write data to there so that they can exchange information. So we have seen a model problem that was using shared memory, producer-consumer problem. In that problem, we have solved that problem using shared memory approach. The producer process was running that code and putting items into the shared memory, and the consumer process was reading the items from the shared memory and reading the consuming the items after reading from the shared memory. So this was one solution using shared memory for this producer-consumer problem. Lots of actual problems are actually in real life look like to this problem, producer-consumer problem. For example, a web server and a web browser is like a producer and consumer, okay? So a solution to this problem is applicable in many real-life scenarios. So let's look to another mechanism that can be used between processes to exchange data, all right? So that other mechanism is message passing. So message passing is another mechanism for processes to communicate with each other and to synchronize their activities, okay? For that, the operating system, the system provides a message passing mechanism. And in this case, what we have, the message passing mechanism establishes a communication link between the processes and through which we can send the message and receive the messages. Then we don't need to use shared variables, okay? So without using shared variables, the message passing system allows the processes to communicate with each other. So it creates something like a pipe or mailbox or something like that. It creates a logical communication link between the process, and the process send and receive messages via the help of the kernel through this logical communication link, okay? If in this way, every message is sent via a system call and received via a system call. So the overhead is a little bit higher, but you don't have to, for example, deal with synchronization problems. There is no danger of two processes accessing the same shared variable in this case. So this mechanism provides two operations for the processes. The process can call these two operations, send and receive. A process can call the send operation, okay? It can be implemented as a system call by the kernel and give the message to be sent, okay? And send system call will send the message to a process, to another process. So a sender process may invoke this operation to send a message to another process. The message can be of fixed or variable size. And a receiver process, a process that would like to receive the message, should invoke the receive system call or function operation provided by the message passing facility implemented by the kernel, okay? So basically we have those system calls, and they are utilized with every information that is to be passed between processes, okay? And if, for example, two processes P and Q wish to communicate, all right, here we see two processes P and Q that would like to communicate, then they need to establish a logical communication link between them and exchange the messages via the send and receive calls through this logical communication link, okay? So this logical communication link is provided by the kernel, and kernel also provides two functions for the processes, send and receive, and these processes use those send and receive system calls or functions of the kernel to send messages to each other, okay? This is the basic approach. So let's look to message passing approach more closely. So assume we have two processes, process A and process B, that would like to communicate. Okay, normally they have, of course, separate address spaces, so they have their own global variables, and the storage allocated to them are totally different. Okay, so they cannot access their global variables and variables directly, right? They cannot access. So each process has its own address space, its own memory. So they are operating on different portions of the physical memory, all right? So they cannot easily exchange data via sharing global variables and so on. So if process A would like to send a message, for example, some data, some information to process B, then it puts that information into a message, okay? It builds up a message, and then it gives the message to the kernel by calling the, for example, send system call, okay? So then the message can be copied into the kernel. It can be buffered there. The kernel may have a buffer that may keep one or more messages, okay? Maybe 10 messages, 32 messages, and so on, depending on the buffer size that the kernel provides. And then, whenever the process B would like to receive such a message, it will invoke a receive system call and will retrieve the message, okay? When it calls the receive system call, then it can get the message that is stored in the kernel. In this way, the message will be available now at process B, okay? So this is the way that the messages are exchanged between two processes. So those processes do not create now a shared memory region. No shared memory is used, but kernel is accessed, message is given to the kernel, and then another process that is interested in receiving the message calls again a system call to receive the message from the kernel, okay? So this is the way that we pass information between the processes in message passing approach. So this slide compares these two approaches, the shared memory approach and message passing approach. In the shared memory approach, we have processes creating, in the shared memory approach, we have processes creating a shared region and then accessing that region directly, okay, using pointers. And then in this way exchanging information. During this time, while they are exchanging information, okay, kernel is not involved. Kernel is involved only to set up such a shared segment, okay? To set up such a shared segment, you call a kernel function, but then you can directly access that region of memory using pointers and write something to there or read something from there. In this way, exchange information, okay? Hence, it's a very fast method, okay? But we have to be careful about accessing the shared variables here. Two processes, if they access the same variable at the same time, then we may have some problems that are called race conditions, and we will see what those problems are and how we can solve them in another chapter, okay, in chapter 6. So in the message passing approach, we have processes not sharing any memory. So if a process would like to send a message, then it gives the message to the kernel, and then another process that would like to receive the message just reads the message from the kernel, okay? In this way, the messages are exchanged by use of the system calls and through the kernel. So every information exchange here requires use of the kernel, therefore it is more costly. But you don't have the danger of accessing this same memory location by two processes at the same time. You don't have such a danger, okay? Because you call a system call that takes the message from you and stores here, and then another process can call another system call and receive the message from here, okay? So the access to that is under the control of the kernel, and the processes does not have to deal with the synchronization and race conditions and so on, okay? So it is easier to program, but it may be performing slowly, more slowly, okay? So let's talk more about the message passing and how we can implement. What are some design alternatives that can be used while implementing the message passing facility in an operating system? So how do we establish the links between the processes? This is one thing that we have to answer and decide on, okay? Whether we would establish the links explicitly or automatically. So we have to answer that question, and we have to decide on while designing a message passing facility. Or another question that we have to think about is, can a link be associated with more than two processes? A logical link, if you create such a logical link, can that be associated with more than two processes? Is it possible that 10 processes can use that link or not? So this is another question that we have to think about and answer that, and then design your message passing facility in your kernel. And how do we establish the links? And how many links can there be between every pair of communicating processes? So if you have two processes, can we only establish one link or can we establish more links? Okay, so this is another question that we have to think. Some systems can allow only one link to be established. Some systems may allow many links to be established between the processes. It's possible. So what is the capacity of a link? How many messages can we buffer? And so on. And what is the size of a message that a link can accommodate? Is there a limit on the size of the message that can be sent through the link? Usually there is a limit, maybe 8 kilobytes, okay? Some systems may not allow you to send messages that is larger than 8 kilobytes, okay? So there is a limit. And also, can the system support variable or variable-sized messages or fixed-sized messages? This is another issue that we have to consider. And whether the link should be unidirectional or bidirectional, okay? This is another question that we can think of. Usually the links are bidirectional, but you can also design a system where a link is just unidirectional, allowing the messages to pass only in one direction from one process to another, not in the reverse direction, okay? So these are some of the implementation questions that we have to think about and then design our system accordingly. So while designing a system, there are these issues that we should consider. Basically the naming. How do we name the recipient? So if you have a message as a process and you would like to send that message, but to which process are you going to send that message? How can you name? Here we have two choices. You can use explicit names, this is called direct naming, or indirect naming. You cannot actually identify the recipient directly, okay, explicitly, but implicitly. So this is one issue that we will discuss a little bit more. And then the other issue is the synchronization. How do we invoke the send and receive and how they operate? In a blocking manner or non-blocking manner, okay? We will see what does it mean. And the buffering issue is what should be the size of the buffer that we will provide, okay, for a link between two processes. We can implement a buffer that has zero capacity or some bounded capacity. And of course, theoretically, the buffer can be unbounded capacity, but it is not practical, of course. So let's look to these issues one by one. So what is direct communication? In this case, the processes must name each other explicitly while sending and receiving the messages. For example, a process that would like to send a message can invoke such a system call where it will send this message to a process P. Okay, so it actually indicates in the system call the name of the P or process identifier of the process. Okay, that will receive the message. Here you are explicitly telling who is the receiver. Okay. You give the ID or name here as an argument to the send system call. You indicate to the system which process should receive the message. Okay, this is explicit naming or direct naming. Or the receive system call issued by a receiver also may explicitly identify the sender, meaning that that process would like to receive a message from that other process, and that other process is named explicitly, directly. Okay, some systems, or you may design a message passing facility having this property. This is one alternative, okay? Then if you do that, what would be the properties of a communication link between two processes that are actually naming each other directly and explicitly? So the links are established in this case automatically. Whenever you want to send a message to a receiver whose name you denote explicitly, okay, then the kernel may automatically create a link to that receiver process, okay? And a link is also associated with exactly one pair of communicating processes. So you send a message to a process, okay, and between you and that process, a link is automatically established, and that link is only established with that pair of processes because they are naming each other, okay? If you name another process, then it would be another link, okay? And between each pair, there exists exactly one link, okay? And that link can be identified between the ID of the sender and receiver. The links may be unidirectional or bidirectional. Mostly it is bidirectional. So this is direct communication. This was one alternative that you could use while designing a message passing facility. The other alternative is this, indirect communication. Here, while sending the messages, as a process, while sending messages, you are not directly or explicitly identifying the recipient, okay? What you are doing is you are creating a mailbox, or there is a mailbox created somehow in the system, and you put just your messages there. While putting the message there, you don't identify or name the recipient, okay? So anybody who is interested in receiving a message from that mailbox, goes to that mailbox and receive the message, okay? In this way, you send and receive messages between the processes. So then the messages are directed and received from mailboxes. Okay. They are also referred to as ports or sometimes message queues. Okay. So a mailbox or message queue or port is a buffer implemented inside the kernel, okay, that can be accessed via the system calls, send, receive, and so on. So you just send your message to there, put your message there. That means you are giving your message to the kernel, and it stores there. It stores it in a message queue or mailbox. Okay. Then anybody who is interested in receiving a message from that mailbox invokes a system call and retrieves a message. Okay. So in this solution, or in this design, each mailbox has a unique ID. Okay, then you use the ID of the mailbox while receiving and sending messages. Okay, instead of using the process IDs. So process can communicate, of course, if they share and access the same mailbox. Okay, if a mailbox is created, then I can put a message there, and another process can retrieve a message from there. In this way, they can communicate with each other. Okay. So if we design our system in this manner, then what would be the communication link property between two processes that are communicating in this manner? So a link is established only if processes share a common mailbox. Okay? If they are accessing the same mailbox, then they have a logical communication link in between. Okay? And a link may be associated with many processes. That means many processes may put message or messages in the same mailbox, and many processes may receive messages from the same mailbox. That means the same link or communication, logical communication link can be used and utilized by many processes. Okay? And each pair of processes may share several communication links. Consider two processes, okay? Then they can utilize one mailbox to exchange data, or if they wish, they can create another mailbox and utilize that. So you may question why we can do that, or what is the use of that, but sometimes it may be easier for the application programmer to think if he or she uses several mailboxes between two processes. For example, one mailbox can be used to send control packets, another mailbox can be used to send some certain type of data packets, and another mailbox can be used to send and receive another certain type of packets. Okay? So in this way, what you can have between two processes several logical communication links or several mailboxes. Okay? So these are some of the properties that you can have if you implement indirect communication. So in this case, let's talk a little bit about how the system will operate if you use indirect communication. So the kernel, as I said earlier, will provide the message passing facility and mailbox facility, right? So this is sometimes called message queue, all right? Message queue is implemented in Unix, for example. You can use the message queues to send and receive messages, but this is the general name, mailbox, okay? So a process that would like to send a message to another process, then first a mailbox has to be created with some ID. Then that process will just invoke a system call, for example, send, give its message to that system call as a parameter, and then also it has to identify the mailbox through which the message will be passed. Okay? So A is, for example, the ID of that mailbox. So when that process invokes such a system call, then the message will be put here. Okay? And then when the other process would like to retrieve a message from that mailbox, it will invoke such a system call. And then that means it's also providing to that system call the same message box ID, A. All right? And then that other process will receive a message from there. Okay? So in this way, this process and that process can communicate with each other using these system calls, send and receive system calls, and a mailbox that is created earlier. Okay? Yes?
Does this mailbox model has any solution to possible problem of conflicting between the messages? Because, for example, the process A may want to send a message to process B, C, and D, but it may also desire to prevent other processes to see this message who share the same mailbox.
Right, exactly. So it is who shares the mailbox should be the responsibility of the application programmer, okay? And if you want, for example, the message to be passed to some other process B, you should have only that process B open the message and get the messages, okay? So the application programmer should be aware that more than one process may open and read the messages. Okay, so therefore it has to design its processes so that only the correct process opens the mailbox. Okay, if another process will receive the mailbox, then maybe we should create another mailbox that will be used for communication between this process and that other process. Okay, if we have 3 processes with which we would like to communicate, then maybe we should create 3 mailboxes. Okay, and in this way we will be sure that if I send a message to A will receive the message, not B will receive the message, okay? Because I am putting the message to the mailbox that is created for communicating with process A, okay? All right, so there are of course some issues in the mailbox approach. So what happens, for example, a process P creates a message, okay? And P2 and P3, those processes also share the same mailbox, a message queue. Then if P1 sends a message, then who will receive the message? Okay? If they opened the mailbox and they would like to receive the message, if both of these processes, P2 and P3, have opened the mailbox and they would like to receive a message, then who will receive the message? Okay? Who gets the message? So it depends on the system. So the system may allow a link to be associated with at most 2 processes. That means there can be at most 1 receiver. Then there is no ambiguity, okay? Since you can associate at most 1 receiver for a mailbox, then if you send a message to that mailbox, that receiver process will receive it, okay? Some systems does not do such a restriction, okay? Then what will happen? If more than 1 process is allowed to read from the mailbox, then systems may synchronize the receive operation so that only 1 process at a time can execute the receive operation, okay? If 1 process calls the receive system call, okay, then another process may call the receive system call again, but the system may synchronize them, okay? The first one who has called will receive the message, okay? This can be another solution. Or the system may arbitrarily select a receiver, okay? Then the sender has to be notified about who has received the message, because there is no guarantee that that process will receive the message or that process will receive the message, okay? Therefore, whoever receives the message, the selection is done in an arbitrary manner. Then the sender may be notified which process has received the message, okay? So these are some of the solution alternatives that we are discussing about message passing. About message passing, another issue is the synchronization. Now, again, we have 2 alternatives here, using blocking system calls or non-blocking system calls, or blocking or non-blocking send and receive operations. Message passing may be either blocking or non-blocking. So what does it mean? Blocking is considered synchronous, and it means this. A blocking send operation, okay, means that you perform a send operation as a process. You would like to send something to the receiver, and you will block until the message is sent, successfully sent to the receiver. That means the receiver has received the message. Unless the receiver receives the message, then you do not return from the send and continue with something else. You wait, okay? Maybe the receiver process is busy with something else. It is not invoking the receive operation, okay? So then you have to wait until the receiver process invokes the receive system call and gets the message from you. Then you can unblock. You are unblocked by the kernel and continue with the other statements after the send statement that you have called, okay? Of course, this is what will happen if we have 0 buffer in the kernel. If we have buffering in the kernel, that means you give your messages and the kernel can buffer some amount of messages, then your send operation is considered complete when you successfully gave your message to the kernel. Then it's up to the kernel to buffer it, store it in a safe place, and later on, whenever the receiver issues the receive system call, give the message to the receiver, okay? In this case, what will happen? The sender will block until it successfully gives the message to the kernel. Do you think that we may have a situation where it has to block? In this case, because kernel has some buffer, right? So you can easily put some messages there. So you invoke the send system call and give your message to the kernel, and you unblock, and you can continue with something else. Can you consider a situation where you have to block and wait?
Maybe sometimes the sender may have to receive a response message.
That's true, yes. If you require that, you have to block. But the other situation is when the kernel buffer is filled up. Because you assume the kernel has a buffer that can hold at most 10 messages. Assume as a sender you put 10 messages because the receiver could not retrieve those, because the receiver process was doing something else, doing some computation and so on, and did not issue the receive system call. Okay? During this time, you generate 10 messages and put them into the buffer, and the kernel buffer is full now. Then in the next time that you would like to send another message, then you have to block, because that message cannot be put into the kernel immediately. You have to wait until kernel now will have some space for your new message. Okay? So you cannot go ahead and assume that send operation is completed successfully. It did not. You could not copy your message into the kernel. So therefore, your process has to be blocked until kernel will have some more space to hold your message. Okay? So if we have a bounded mailbox inside the kernel, then sooner or later the sender may block, because that mailbox may be filled up if the receiver is not retrieving the items. Yes?
Those messages get deleted after first read?
After?
Read once.
Yes, exactly. So if the receiver retrieves a message, that message is deleted. Okay? So that consider kernel gives the message to the receiver and it deletes it from its buffer.
You cannot read it twice.
No. Usually every message is actually received only once. So this is the blocking send operation, how it operates. If, however, this does not have to be always like that. You can use non-blocking system calls and non-blocking send operation. That means you can invoke the send operation. Okay, it will return immediately. What does it mean? In some cases, it will return immediately and with success. In some cases, it will return immediately but without success. If the kernel buffer is full, it will return immediately without success. It could not copy your message actually to the kernel buffer yet, okay? But it has to return because you are using send system call that is non-blocking. Okay, you can convert a system call to non-blocking mode. Okay, this is possible. And then develop your program accordingly so that you will not block in a system call. But then you have to check the return code of or return value of those functions, kernel functions, send of those system calls. You have to check after you issue the send, okay? You have to check the return value. Return value will tell you whether send was successful or unsuccessful, okay? Depending on that, then you can do something else. If it is successful, then you can assume that your message has gone, okay, correctly, and you can maybe generate another message and try to send it. But if send returned you a value that the send was unsuccessful, then you cannot get rid of your message. You have to come back later on, try again. You will try again to send your message to the kernel and finally to the receiver. That means you have to again issue the send system call with the same message, okay? So the application programmer is responsible now in designing his program with non-blocking system calls, doing the checks and so on, okay? So, but you have two alternatives, using blocking send or non-blocking send. Similarly, for the receive operation, we have the same thing. You can use the blocking receive or non-blocking receive. What is the blocking receive? In the receiver process, in the process that should receive the message, okay, then what you can do, you can call a receive system call, receive function that is blocking. That means it has to block the calling process until the message is received. If I am a receiver expecting some message from a sender, okay, if I call the receive operation, then I wait at that statement, like waiting, for example, at scanf. Okay, in scanf you wait until somebody hits the keyboard, right, and gives you some input. You cannot go and continue execution, right, in the scanf until somebody actually presses the keyboard keys. Similarly, in the blocking receive, you wait until message arrives. If the message never arrives, you can never continue. Okay, so you wait until the message arrives, and when the message arrives, when there is a message to be retrieved in the kernel buffer, then you get the message and you have the message and continue with the other statements after the receive system call, okay, in your program. So this is how receive would perform and would act. So, of course, at the time that you call the receive operation, if there is a message in the kernel, then immediately that message can be retrieved and receive will return immediately and you can continue with other statements after the receive, okay? So this is how blocking receive will behave. What about non-blocking receive? You can, as an application programmer, you may want to use non-blocking receive operation because you don't want your application to be blocked for an undeterministic amount of time at the receive operation. As an application programmer, you may decide that, okay? Then you can use non-blocking receive operation. In this case, what will happen? You will call the receive operation, it will immediately return. So what can be the result code? Return value. It may indicate either success or unsuccess, okay? If it is success, that means that actually there was a message in the kernel buffer at that time, and the receive operation could retrieve that message, okay, to the application. But if there were no messages at the moment that you have called the receive operation in your application, then what will happen? The receive again will return immediately, but with a code indicating there was an error, an unsuccessful operation, okay, because no message could be retrieved. So depending then, as an application programmer, you have to check the return value and act accordingly. If, for example, the check indicates that it was a successful operation, then you can assume that you have the message and you can process the message. Otherwise, if the result is unsuccessful, that means you cannot assume that you have a message now. You have to go and do something else and maybe retry later on, okay? So retry to receive a message, issue the receive system call again, hoping that at that time a message has arrived and you will be able to retrieve that, okay? So it is the job of the application programmer to do these checks. So non-blocking receive has the receiver receive a valid message or nothing, okay? And you can understand what has happened by checking the return value of the system call that you have called, the receive system call, okay? So these are the issues, synchronization issues that we have to consider. So the operating system may provide, for example, both types of system calls, non-blocking and blocking send and receives, and then depending on what you have as the application programmer, you can program your programs accordingly, okay? Another issue is the buffering. How much buffer you should provide in the kernel to buffer the messages. In other words, what should be the size of the mailbox? How many messages it can keep, okay? Sometimes you may choose to implement zero capacity buffer. That means you will not buffer anything in the kernel. Then, whenever a sender sends a message, the receiver should take the message and then the operation is completed. The sender cannot give the message to the kernel and kernel will not buffer that, okay? So the sender has to wait until the receiver get the message from that if the sender is using blocking system calls, okay? So this is the zero capacity buffer. Sender must wait for the receiver if the sender is using, of course, blocking system calls. The sender cannot assume that operation is completed when because there is no buffer in the kernel to buffer the message. So it is not enough to just take the message and buffer it in the kernel because there is no buffer, okay? The sender has to wait until the message that's generated is actually received by the receiver. Then the sender can assume that operation is completed. Otherwise, if you would have a buffer, then the sender was thinking that the operation is completed whenever it could pass the message from itself to the kernel buffer. Then it can assume that sooner or later the message will arrive to the receiver. But in this case, if we have a zero buffer, we cannot assume that. In the second alternative is implementing a buffer that is of bounded capacity, and this is the usual approach that's followed by most of operating systems. So we, in message queues that are provided by Linux, for example, can store some messages, but there is a limit on the number of messages that you can store in a message queue in the kernel, okay? So we have a finite length of n messages that can be stored in the buffer. And sender must wait, of course, in this case, if the buffer is full. Otherwise, whenever sender invokes the send system call, the message can be just taken from the application and put into the kernel buffer. But if that buffer is full, this cannot be done, so the sender has to wait. If it is using blocking system calls, of course, sender has to wait if the link is full and until there is again a space in the link or buffer for any message, which will happen when the receiver process invokes the receive system call and retrieves one or more messages. Then we may have enough space in the kernel buffer to hold any message that is to be sent by the sender. Or theoretically, you can have an unbounded capacity buffer, which is never getting filled up, okay? So infinite length buffer. Of course, this just can happen in theory. You cannot have a practical system like this. If you would have that, then what will happen? The sender would never block, never wait, whether it is using blocking system calls or non-blocking system calls, because we always have buffer to store any message. And the kernel can get the message from the sender and store it in its buffer without any problem at any time, because the kernel has an unbounded capacity buffer. Okay? So these are the issues that we have to consider while implementing a message passing facility and providing it to the applications so that the applications can exchange data in between. Okay? Any questions so far? Okay, let's look to some examples. Okay, so we will give some examples from the Linux operating system, and for the shared memory, what facility Linux or Unix provides as shared memory so that the applications can use that to exchange data. There are actually two different application programming interfaces, APIs, that are provided by the Unix and Linux operating systems. There are two different APIs that provide functions for shared memory operations, okay, in Linux or Unix, okay. So one set of functions, one API is called System5 API. The other set of functions, the other API is called POSIX API. You know what POSIX is, right? This is the standard API that a POSIX compliant operating system should have. POSIX means Portable Operating System Interface. It's a standard API for Unix-like systems. So if you write a program that uses POSIX functions, then it can run in any operating system that is POSIX compliant. Okay? So this is the goal of the POSIX standard. It tries to standardize the API, the functions that can be called by the application programs to invoke kernel services. Okay? So POSIX API has a shared memory, has some functions to create a shared memory and use that. And also there is another API called System5 API. So what's System5 API? System5 was actually one of the earlier Unix operating system versions. All right. So it is developed by AT&T and so on, a company. AT&T has developed System5. It was an earlier version of Unix that has introduced actually the shared memory idea, and that has implemented it in the operating system. Okay. So this is the one of the earlier Unix versions that introduced the shared memory approach and implemented it in the operating system. So therefore, we have System5 API and POSIX API. The basic idea is the same. Both create shared memory, okay, between processes. Both APIs can be used to create shared memory between processes, but each has a different function. Different set of functions are included in each of them. Okay, so you have to learn what functions are there if you want to use one of these. So let's look, for example, the System5 shared memory. System5 shared memory has such functions to create and manipulate or manage shared memory. One function is shared memory get, another function is shared memory attach, another function is shared memory detach, and so on. Okay, whereas the POSIX API has such functions: shared memory open, shared memory unlink, ftruncate, mmap, and so on. Okay. So you have to, if you would like to program, you have to read the manual pages of those functions and understand what they are doing, and then you have to use in your programs them to write programs that are using shared memory. Let's look, for example, how we can program using System5 API. So if you want to create a shared memory using System5 API, then you invoke the shared memory get function. Okay. Here it has several parameters. Size is the size of the shared memory that you want to create. It can be, for example, 32 kilobytes. Okay. As a result, what is returned is an identifier is returned to you. Okay, so that you can use it in other functions that are invoked regarding that shared memory. So after that creation of the shared memory, the process can do what? The processes can use that shared memory. Before using that shared memory, or in order to use that shared memory, every process has to call the shared memory attach, okay, SHMAT function. This actually attaches the process to the shared memory. What does it mean? It is actually providing or giving to the process a pointer. So the return value of that function is a pointer, okay, that can be stored, for example, in the process, in one of the variables of the process. Okay, so with that pointer, actually now after that point, you can use that pointer and access the shared memory. Okay, you know the pointers, C pointers, and you can use the pointers. Pointers are memory addresses. You can use them to write something into that address. Okay, to put some value there or read values from there and so on. So this pointer is a pointer to the beginning of the shared memory that's created. And when you have that, since you also know the size of the shared memory, you can access actually using that pointer any location, any byte of the shared memory after that, okay? So after this call, now the process is ready to use the shared memory. It can, for example, write a string like this. It can use the sprintf function of C to write a string like that into the shared memory, into the memory area that is pointed by the pointer that is returned from this function, okay? So then, from now on, you can access the shared memory, write something there or read something from there, okay? Ordinary memory access. But you use pointers for that, okay? And when you are done, then you should detach the shared memory from your address space. And this can be done by calling the shared memory detach function, okay? And you give your pointer to the shared memory, and then this function will just remove the shared memory from your address space so that you become no longer be accessible, you can no longer access the shared memory. Is it clear? So any process, there may be, for example, 10 processes that may issue that call, okay, and have a pointer in their address space, which can be then utilized to access the shared memory, okay? Of course, you store that pointer in a global variable, in one of your global variables, and then you use that global variable, pointer variable, then to access the shared memory, okay? So this is what we can do in System 5 Shared Memory API. If you would like to use the POSIX Shared Memory API, then these are the functions that we can utilize, okay? What are those? Let's look briefly at them. Shared memory open can be used to create a new shared memory region or open an existing one, okay? Shared memory unlink can be used to remove a shared memory region. Sometimes it's called shared memory object, okay? Shared memory region, shared memory object. F-truncate can be used to define or set the size of the shared memory. After creating the shared memory region with that, you can use this function to set the size of that. For example, you can set the size of the shared memory to be 64 kilobyte or 1 kilobyte or just 50 byte, okay? Whatever you give as an argument to here, that will be the size of the shared memory that is created, okay? Then, similar to the function here, shared memory attach function, you have to call mmap function to get a pointer, okay, which can be utilized afterwards to access the shared memory, okay? So mmap is memory mapping. It actually maps that shared memory region, created region, into your address space, okay? So that some set of addresses in your address space are used to access that shared memory. So whenever you use those addresses, that means you are actually using accessing the shared memory. Hence, the first address or what is returned by mmap is the start address of the region in your address space to where the shared memory is mapped into, okay? Then, with that pointer, you can access the shared memory. So the mmap maps the shared memory segment into the address space of the process that calls that. Several processes, 10 processes, can call that and obtain a pointer which they can use to access the shared memory, okay? With this, a process gets a pointer to the shared memory region and can use that pointer to access the shared memory region, all right? So there are other examples for interprocess communication in other operating systems. In Mach operating system, for example, message passing can be used, and we can have calls like message send and message receive operations like that to send and receive messages, okay? And the book also gives example for the Windows, how the IPC is done in the Windows, but we will not go on that now. So this was about the communication between processes in a system. So message passing and system shared memory was two basic approaches that can be used by processes to exchange data in between, okay? But those processes has to be sitting or running in the same machine, okay? In the same computer. Any questions so far about those two facilities? Okay. So now we can start a little bit different discussion, which is the communication facilities that we can use for communication between processes that are not running in the same machine but running in different machines, okay? So sometimes those processes, one of them act as a server, the other act as a client. For example, a web server and a web client, okay? A browser is a web client, and a web server, Apache server, for example, is a server, okay? So basically, those facilities that we will describe briefly now can be used for those kind of processes to communicate with each other. They don't have to run on the same machine, okay? So we will just briefly talk about three methods here: the sockets, remote procedure calls, and remote method invocation. Of course, these methods or these mechanisms can also be used for processes and communication of processes in the same system. Two processes can be running in the same system and still can use the sockets or RPC or remote method invocation to talk to each other, okay? To exchange data. But these facilities work if they are running actually in different systems as well, okay? In the previous approach that we have described, the message passing approach and shared memory approach, they are actually valid approaches if the processes are in the same machine. If the processes are running in the same machine, then you can use the shared memory approach. Otherwise, if they are on different machines, there is no memory that's shared, okay? So let's look to these approaches after the break, okay? So let's have a 10 minutes break and we will continue.